Hello, Marvelous Algebra 1 students, and welcome back. We are starting a new topic today. Topic 3 is on linear functions. This is going to be a pretty quick unit. We actually only have 4 lessons. Our first 2 lessons are all about what are functions, and then a bit of what's called function notation. And then our last 2 lessons are going to use our newfound knowledge and tie it back into what we did last unit with some graphs. So, without further ado, let's go ahead and get started. Our goal for today is just to describe properties of functions. Essentially, what is a function? And then there's going to be a heavy focus on domain and range, and then the idea of the difference between discrete and continuous functions, or just relations. So, bunch of vocabulary today, and then a bit of practice at the end. Shouldn't be too terrible. In fact, you should already know what a function is, so maybe a lot of this lesson won't be new, and hopefully it's a quick and easy one. So, you can examine the relationship between any two things you want. Sometimes they are related, and other times they're not. These things are more commonly known in math as quantities or variables. And we will just like to see if there's a connection between those two things. For example, imagine you created a table that contained, and when I say a table, I mean something like a table like this. And you don't need to write this down, but there would be an input and then an output. It's a pretty common table. Okay, and imagine you created a table that contained the heights of everybody in this current class that you're sitting in one column H. Maybe I'll call this H over here. And then the corresponding name for each person in the second column. So we'll call this N for name. Pairing H with N is known as a relation. Okay. If I tell you that each pair of names and heights is ordered, then in an ordered pair, H, N, the order of the values is important, right? If you put something like 4, 7, that would be different than 7, 4, because this position is always the H and this position is always the N. Of course, those values don't make a lot of sense for height and names, so let's look at a quick one. I could give you my height as an input, and just in case you're curious, I'm 5 feet 9 inches tall. And then, of course, the output would be my name. And in this case, my name would be Mr. Grant. Easy enough. Okay. In math, the set or the list of all of the inputs are commonly known as the domain, while the set of outputs are known as the range. We usually list the values of domain and range using these cool little curly brackets, and I've heard them called curly brackets before. Most commonly they're called braces when they are curly like that. I always joke and call them sideways seagulls. You know, when you draw a bird, you kind of do something like that, so I call them sideways seagulls. So, in the context of the example that I gave you, what would the domain represent? Well, the domain in this case would represent, and notice my input here was H, it was the height. My domain would just be a list of all the heights. And the range would be the list of all the names. So if there are 36 people in this class, in these curly braces, or in these curly brackets or braces, you would record the name of everybody in your class. And in this other set, you would record the height of everyone in that class, and in the other set you'd record the name. Alright, well, we can narrow down our relations to a very specific type of relation that we say is well-behaved. Well-behaved is like well-defined. It fits a certain definition that we're going to go over, and that is the idea of a function. Okay? The idea for a function is this. If you're given an input, then you can tell or determine without a doubt what the output is. Notice our relation example above, where I talked to you about the heights and names, is not a function, right? If I gave you an input of something like 5 feet 6 inches and then asked for the output, I bet there's more than one person in your class who's 5 feet 6 inches tall. Maybe this belongs to Devin. maybe it belongs to Lily, maybe it belongs to both of them. But if I say 5 feet 6 inches tall, if you can't definitely tell me the exact one person that this maps to or corresponds to, then this is not a function. Now, that might sound a little confusing, so I'm going to give you a quick story about pizza to really hammer home the idea of a function versus just a relation. Okay, so let's say that we have 3 people. Let's take Kirsten, Erica, and Daniel. Okay, and they all walk into a pizza place one day because they want to study for their math tests like good humans. And they walk in and they realize that there's a cool sale going on for pizzas, right? And they're like, okay, this sounds awesome. We are all feeling the same type of pizza, but we're going to order individual pizzas just so we have leftovers. So they chat and they're like, yeah, we're all just feeling a regular pepperoni pizza. So Kirsten walks up to the counter and she says, hey, guy says, how's it going? She goes, yep, yeah, I'm going super well. I would like to order a 1 large pepperoni pizza. So her input at this point, right, her input is going to be 1 large pepperoni pizza. And the cashier says, okay, that's awesome. That is going to cost you $10. Great. Well, then Erica walks up and she's like, well, I'm also feeling a large pizza. And the guy says, well, I got to tell you, we actually have a special going on where you can get any large pizza with a single topping and it'll be the same price. And Erica says, oh, good, because I actually kind of changed my mind about pepperoni and I'm thinking that instead of pepperoni, I'm just going to get a pizza with sausage on it. So she orders 1 large sausage pizza. And the cashier says, okay, sounds good. That is going to cost $10. Awesome. And then Daniel walks up. He says, same thing. I would like an input of, let's see, 1 large. And maybe he just wants a double cheese pizza. So cheese is extra topping here. Sounds good. And they say that the output is, okay, also $10. Well, this would make sense. This is considered a function because you can take an input and you can see an output. If I were to say, what does 1 large pepperoni pizza cost? You could say that's $10, right? You could say, what's 1 large sausage pizza? That's $10. Nothing too bad. Now, going backwards would be a little challenging because if I said, what kind of pizza costs $10? Well, I don't know the one specific answer. However, it works this way because with a function, we only look at the input, and we just want to make sure the input only matches to one output. Now, what would be something that's not a function? Well, let's say that you walk into some shady pizza parlor in town, right? And you've heard some bad rumors about them. Well, same people, Kirsten, Erica, Daniel, decide to meet up the next week. They're also all feeling pizza. They walk into this shady pizza parlor, and they're each going to order their own again. They enjoyed the leftovers. Nice leftover pizza for breakfast, cold pizza, yum yum. But this time they decide they all want the same pizza. Kirsten's pepperoni looked good last time, so they're going to do the same thing here. So Kirsten walks up, and she exchanges her pleasantries with the cashier and says, okay, I would like 1 large pepperoni pizza. And the cashier says, okay, sounds good. That will be $10 for you. And she says, okay, sounds good. No new surprise. Erica now walks up to do the exact same thing. And she says, okay, I would also like 1 large pepperoni pizza. And the cashier says, okay, for you, great, but that's going to be $15. Erica's a little bit confused, but says, well, that seems very strange to me, but I'll think about it. And so Daniel walks up, does the same thing. He's like, I would also like 1 large pepperoni pizza. And the cashier says, awesome, for you, that's going to be $5. Well, this would be the idea of something that doesn't make sense, right? We have a function where you have an input, and it's the same input every time. And with a function, I should be able to give you an input. In this case, the input is a large pepperoni pizza. It doesn't matter who ordered it, and it should only match to one output. It doesn't make sense for a large pizza to match to 3 different prices. Now, I know students in the past have said, well, they could have had coupons, or, maybe they got a discount for something before. Yes, you're right, but I think that's also not the point of the story. You probably understand the point that an input can't map or match to multiple different outputs and still be a function. We need to, if given an input, be able to tell exactly what the output is. Now, we're going to refer to most of our equations or relations as functions from here on out. Um, they're not all going to be functions, and I'm going to slip up and I'll do my best to call them relations instead of functions, but you'll get the idea. Any vocab, though, that we use for functions is also going to work for relations, so it shouldn't be too terrible. We're going to go ahead and divide our functions into two different categories. We have continuous functions, which we've actually seen quite a lot in this last unit. For example, continuous functions would be something like a friendly line. This was a continuous line. It's a line that goes forever. Sometimes these continuous functions don't always go forever in each direction, but the general idea with continuous functions is you have lots and lots and lots and lots of points, an infinite number of points, and instead of writing all of them, we just shade them together for a line, right? A line is made up of an infinite number of points. It just gets tedious to write all the points on there. Sometimes these continuous functions can have discontinuities or little gaps, right? Sometimes you could have a line right here that has this little gap and then continues on the other side, right? This open circle, and we've seen the concept of an open circle before with number lines, means that we're basically just skipping over it. We can't use it. There is nothing there. And so what you could do is you could think of that, if we go up, as literally just a gap. But then the question is, how big is the gap? So we just use the circle to show that the gap is just the length of one point. There's one point that's missing. We still count this as a continuous function. These little gaps are known as discontinuities. That's our fancy term, but that's not really the most important thing for today. Just continuous function, lots of points connected with a line. That's contrary to our discrete functions, where a discrete function is where the values are distinct and separate. It means you have unconnected points. So, for example, it might be a graph that just contains 4 different points like this. Those 4 points could be in a line as well, but we're not going to connect them because there's nothing in between. There's a countable number of points. So for our lesson today, we're going to start by looking at discrete functions, just because I think they tend to be a little bit easier. And then we'll finish off with continuous functions. So what we're going to do for these next 4 problems is decide if each set of points, and these points are going to be presented in different ways, maybe in a table, maybe as a set of points, maybe as a relation mapping that we'll see shortly, and we're just going to decide if they are a function or not. And then we're going to state the domain and range. So let's get to it. Here is our first possible function. We have our x's, and with a table we always think of the inputs on the left and the outputs on the right. Traditionally we use x for an input, y for an output, but we don't have to. Alright, first off, we have points in the table. Is this a function? Well, when you're looking to decide if something is a function, you just look at the inputs. Right, and you ask yourself the question, if I told you the input was -2, would you know without a doubt what the output is? And as you look down this table, there's only one -2. It only goes to one number, so sure, we know that the output for -2 is 4. And we do the same thing for the rest. There's only one -1, so that's an easy output. Only a single 0, single 1, single 2, single 3. Great, this is a function. What is my justification? Well, there's a few different ways to do this. You could just say each input, each x, only maps or only connects to one y. Sometimes people will think, and I wrote this up above, that the inputs didn't repeat, so therefore this is a function, right? So we're just looking to see if any of these numbers or values repeated here. So however you'd like to say it, I'm just going to say each input only maps to one output. What do we do for the domain and range? Well, my domain here, oftentimes you'll just see the letter D for the domain. We're going to use that cool curly brace. We're just going to list all of the values on the input. Now I see 6 different values. We like to list this input from least to greatest. The smallest number here is -2, then -1, 0, 1, 2, and 3. Great. There is my domain. That's it. I listed all the values that are inputs. Then we list the range. Now the range can be a little trickier. at least in this case, because first we like to go from least to greatest. The smallest number for the range is 0. And then second, notice that there are two different ones here. So we don't actually write both ones. There's no reason to do that. We're just listing what specific answers could you get. You could get an answer of 0. You could get an answer of 1. In fact, you can get an answer of 1 twice, but we just write that once. You can get an answer of 4 and of 9. So we don't list the repetitive values, right? They're all contained right here. And so you could ask yourself, if there's an input of 0, what is the output? Well, looking at the table at 0, and notice that maps to a number in the range. Okay? You could say if you have an input of 1, what's the output? Well, the output is 1, so it maps over here. If there's an input of -1, what's the output? Well, that also maps to 1. It's okay if two different numbers map to the same output. Think about our pizza example. You can order two different pizzas and have them be the same price. All right, let's try another. This time, instead of seeing points as a table, we're going to see points as just a point, or a set of points. This is going to be points as sometimes this is called a set. They're already in these curly braces. So let's decide, do these points make up a function? Well, we look at all the individual inputs. 2/5, in case you need this on your calculator, is 0.4. We have this guy, this one, and this one. I don't see any repeating inputs. They're all different inputs, which means we're going to know their outputs, right? If I say the input's -3.5, do you know the output? Sure. There's only one -3.5 on here, and it maps to 6. Sorry, I'm tired, old, and I should have been in bed hours ago, I guess. So, yep, this is a function. Each input maps to one output. And then same thing again. We're going to list the domain. What's our smallest number here? Practice those negatives. Looks like -3.5. Next smallest, -2.1. Then -1. So I took care of those. Then we have 2/5. And last but not least, 3. Last but not least, we have our range. Smallest value for the range looks like -10, and I just cross them off so I know that I'm done with them. Then we have -1, 1/5, and then notice we have 2 6s, but we just have to write that once. And I think that takes care of it. Wonderful. All right, let's move on to the next page. On this next page, your teacher is actually going to pause this really quickly. Or you're going to pause this really quickly if you're watching this on your own, and you're going to try C and D. If you need help from your neighbors or you need to look back at your notes, that's totally fine. Once you're done with C and D, you're going to unpause this, and you're either going to skim forward to see if you did it right, or you guys can share out answers, or you can just watch me explain it. Ready, set, go. All right. Well, one way that you've probably seen before to handle inputs and outputs is with what's known as a mapping relation, where the mapping relation takes the input and it shows you with arrows what that input maps to. So for example, this 1 maps over to 2. If you input 1, you know that the output is 2. Okay? So the first question we need to ask is, does this relation demonstrate a function? And I think you just need to ask yourself a question. If you know the input is 1, do you know the output? Certainly. If you know the input is 2, do you know the output? And no, you don't. 2 has 2 possible outputs here, and that's a no-no for a function, right? That would be like walking into Port of Subs and saying, right, Port of Subs numbers their menu, and you say, walk into Port of Subs, you're like, I would like a number 2. And then depending on the time of day, they're like, either that's $4 or it's $8. Well, that doesn't make sense. Yes, I know you could talk about different sizes, small, medium, large, but we're just assuming that this is a number 2, whatever size, could either be $4 or $8. We can't have that uncertainty. So this is not a function, and the reason why is because 2 maps to both 4 and 8, and I think 3 maps to both 6 and 10. So we have an input that goes to 2 different outputs. If you saw this at points, this would be like the point 2, 4 and 2, 8. The input would repeat with different outputs. However, even though this isn't a function, it's still a relation, and we can still write a domain and range. Right? Our domain here is not too bad. It's just the inputs of 1, 2, 3. And our range is also not too bad, from least to greatest, 2, 4, 6, 8, and 10. All right, let's try this last one. Is this a function? Well, it might help you to write out what these points are. For example, this first point is 1, 5. My second point is 3, 5, 4, 2, and 6, -2. We look at each of the inputs and say if we know the input, are we guaranteed an output? Well, 1 maps to 5. 3 also maps to 5, and that's okay. Having the same output is fine. And the reason that's fine, again, think back to Porta Subs. If you order a number 1, that can be $5. If you order a number 3, that can also be $5. That's okay, as long as we aren't repeating any of the inputs. 4 maps to 2, 6 maps to -2, so we'd say yes. Each input has only one output. And then hopefully you're pretty comfortable with the domain and range at this point. That's not too bad, right? 1, 3, 4, 6. The range can be a little tricky because we have to go least to greatest. So one trick for that is the domain, least to greatest, the number line goes this way. So you just read from left to right of all your points. So I went 1, 2, 3, 4, but just the x's. When you do the range on a graph, the y values start small from the bottom and get larger. So I want to work my way up. My smallest one is -2, and then as I work my way up, my next one is +2. Then keep working your way up. The last one is the same output, which is 5. Okay, so this really concludes our discussion on discrete functions, individual points. Continuous functions can be a little bit trickier. And the reason they're a little bit trickier is because there's an infinite number of points there. And when you're dealing with an infinite number of points, in particular, the domain and range can be a little bit harder. There's actually two ways to write the domain and range for continuous functions. One way will be familiar to you. You can use what's called set notation. And we're not actually using full set notation this year. You'll learn that later on in your math career. But we're just going to assume that set notation means you're going to be using inequalities, which we've done before, right? For example, you could say all the x's that are on your graph are the x's starting at 0 and ending at 4, equal to 4, but not equal to 0. And we'll see what that looks like on a graph. And then, if you were talking about the range, which are the outputs or the y values, you could say all the y values on the graphs are the ones that are equal to -1 or greater than -1. The new notation for you right now, which will be more commonly used in the future, but you are expected to know, is called interval notation. Interval notation uses parentheses and brackets instead of these less than or equal to or greater than or equal to. So for example, if you had x which was greater than 0 but less than or equal to 4, it would look like this. We wouldn't even use an x anymore. We would just have a 0, 4. Now, we aren't going to just sit here and put this in parentheses. This isn't a point, though sometimes it does kind of look like that. What we do here is, if you are just greater than or less than a number, we just put a parenthesis. That tells us we start at 0, but we're not equal to 0. Then, when we end at 4, because we can be equal to 4, instead of using a parenthesis, we use what's called a square bracket. So that's kind of some weird notation. As soon as we see that, we know that this is telling us that x can be between 0 and 4. Well, how do we know we're talking about x instead of y? Sometimes you'll see a d in front to represent the domain. But then, how does it work for this guy over here? Because we always like to write our domain and range from least to greatest. 0 is smaller than 4, so 0 is on the left, 4 is on the right. Well, if we're dealing with something like this where y is greater than or equal to -1, the smallest number here is certainly -1. But what's the largest number? Well, greater than negative 1, anything greater. What's the largest number that you can think of greater than negative 1? As a hint, it's not actually a number. Yeah, maybe you're thinking about that sideways 8, or the more technical term is infinity. What this tells us is that y can go from negative 1 all the way up to infinity. Y can be equal to negative 1, so we use a square bracket facing this way. And then the weird part with infinity is that infinity is not actually a number. It just means go forever, right? You can't count to infinity. It's not the last number you can ever get to. It just means keep going forever. And so since infinity isn't a number, it's just a concept, we can never be equal to infinity, so infinity always uses a parenthesis. Now, let's go ahead and see what this actually looks like in practice with 3 continuous graphs. You'll notice, of course, that these are continuous because we don't have individual points. But remember that this graph actually has an infinite number of points on here, right? You could list any point that you wanted, and as long as it was on this line, that would be one of the points that's graphed. For example, right, we've talked about looking for nice points, and there are some nice points on here. There's a point right here, and right here, and right here. But there aren't just nice points on this graph. There's also, I don't know, even this point right here. This is the point 1 comma negative, looks like negative 1.5. This would be, probably would map to a negative 1.6, negative 1.7, 1.8, 1.9. Now we're at negative 2. So an infinite number of points, and that becomes important. So the first thing we're going to do is list the smallest and the largest inputs on this graph. So that's a fancy way for input, right, is listing the x's on this graph. So how do you do that? Well, just let's start with the smallest x value I see on my x-axis. The smallest x value I see is negative 3. And I would ask myself, is there a point on this continuous line that has an x of negative 3? And the easiest way to do that is just to kind of track down and see where you cross over the line. Well, I mean, here is a point negative 3 comma negative 3, but that's not on my graph, right? That's not shaded in, that's not connected, it doesn't fall on my line. So I think, in fact, negative 3 isn't even on there. What's the smallest x that is on there? Well, hopefully you said, oh, negative 2. And you're right, because this is the point negative 2 comma something. We'll fill in the something later. I think the smallest x that's on here is negative 2. What's the largest x? Well, you might be tempted to go over and say, ooh, 2. 2 is the largest x. And you're right, there is a point 2 comma something. But what does this arrow mean? This arrow means that the graph continues to the right. And so, and don't write this because I'm going to erase it, technically this x-axis goes forever over here, and my graph goes forever up and up and up. So not only is there an x of 2, there's an x of 3 and 4 and 5 and 6 and 7 and 8 would be on the graph, and so on and so forth. So what's the largest x that's ever on the graph? Well, because this goes to the right infinitely far, the largest x on this graph is actually infinitely large. So how would we show infinitely large on the x-axis? Well, you can just put a little infinity here and draw maybe an arrow to remind you. So the largest input for x is actually going to be infinity. Let's go ahead and do the same thing for the outputs. All right, the largest and smallest outputs. Well, if you look at the y-axis, again, the y-axis goes up and down. The smallest y's are at the bottom. There's no y of negative 4, though, because negative 4 doesn't end up anywhere on my line. However, there is a y of negative 3, and it won't shock you too much that this y value is right here. So my smallest y, the lowest my graph ever goes, is a y value of negative 3. What's the highest the graph ever goes? Well, if there wasn't an arrow there, you might just kind of go up and say, oh, this is like the ceiling, this is the top that our function ever reaches. And some will be right. It looks like it only gets up to negative 1, except for that pesky arrow. That arrow again means that this goes up and up forever. And so because it goes up and up forever, it's going to get to the very tippy top of the y-axis. The largest value on the y-axis is also going to be infinity. So y is going to be infinitely large. All right. So how do we actually write this using our set and our interval notation? Well, the set notation I think tends to be a little bit easier for students to start because you've used these before. How would you describe the x's that are on this graph? Well, the x's start, and I should say x, the x's start at -2 and they get bigger, they get greater than -2, right? They go from -2 to infinity. So we say x is greater than or equal to -2. How do we write this in interval notation? Well, interval notation has to use the smallest and the largest. So I'm going to use both of these, -2, comma, infinity, least and greatest, left to right. Then we ask ourselves, could x ever actually be equal to -2? Well, certainly, there is a closed circle right here. That means there's actually a point there. And so we can be equal. And because we can be equal, we use that bracket. Right? And if you wanted to draw a little arrow, that's because there's an equal to. Then we say, well, what's the largest x? Infinitely large. Can x ever be equal to that? No, because x cannot equal infinity. That's not actually a number. Even saying equals up here isn't particularly correct, but that's all right for today. I'm just going to put a parenthesis here. And it is good to put that D for domain at the beginning. All right. Do you think you can figure out the y's? They're pretty darn similar. Our smallest y is -3, and we just grow greater than that. So our range here is that y is greater than or equal to -3. And then in terms of interval notation, we go least to greatest. We can be equal to -3, but not equal to infinity. Two different ways to say the same thing. All right, let's try this next one. And before you jump into the next one, and I am going to have you guys try it, you should notice that there are two different things about this equation. First, the arrow is pointing down, so we're going more and more negative. Second, the starting point here, instead of having a closed circle, does have an open circle. And I am going to draw your attention to that. That's an open circle. And I know it's kind of hard to see on your paper because it's fairly small there, but it's an open circle, and that is going to change things just a little bit. However, what I'd like you to try and do is the same thing that we did on the first graph. So identify the smallest and largest outputs, and then if you're feeling bold, try the domain and range. Just write lightly in case we have to erase anything. Once you've tried that, maybe after a minute or so, you can unpause the video and see how you did. Ready, set, go. All right, let's go smallest and largest outputs. Well, this one is definitely a little bit weird because this graph goes down forever. So if we think about the x-axis, the largest x is pretty easy, right? There's no x of 1 on your graph anywhere. There's no x of 2 because it stops at an x of 0. This is the point 0, comma something. So I think the largest x on this graph will be 0. What about the smallest? Well, there's a point with -1, a point with -2, a point with -3, but it goes down forever. So there'll be a point with -4, -5, -6, all the way down, 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 down. What's the smallest x that will ever be on there? Well, if you go to the left side of the x-axis, all the numbers there are negative. I think the smallest x will be -infinity. All right, let's do the same thing with the y's. Well, if we think about the y-axis goes up and down, the largest numbers will be the highest up the graph ever gets. The highest up the graph ever gets is this kind of ceiling right here at -2. So I think the largest y is -2. And then notice there's a y of -3 over here, a y of -4, and in fact, because the graph goes down, down, down forever, the y will be -infinity. But I guess I should have put the -2 there. All right, let's try for that domain and range because things are a little bit weird here. So, domain-wise, it seems like the x's that are on here are x's from -infinity to 0. Another way to think about that, though, is that the x's are just less than or equal to 0. So I'm going to have an x and a less than and a 0. But I want to pause and consider that equal to 0. Can x actually be equal to 0? Over here, x could be equal to -2 because there is a closed circle. And we've seen before with inequalities, when there's a closed circle, that means that the variable can be equal to that. However, when we had open circles, that was a case when the variable could not be equal. It was just the starting point, but we couldn't actually use that point. And it is the same thing here. If there is an open circle, we cannot put that equal sign underneath. X can't be equal to it. It's just a starting point, right? And I'm just going to put this little over here, and I'm going to say no equals open circle, just so you remember for your notes. Now, the nice part is the interval notation is pretty easy that way. Since we are going from negative infinity to 0, least to greatest, left to right, we can never be equal to infinity, that's fine. And then we also can't be equal to 0, so it's really just two sets of parentheses. We know this isn't a point, though, because we have that domain out front. It's showing us this interval. Let's try the range. Okay. Our range here, well, let's see. It looks like we start at -2 and go below -2. So our y values here are going to be less than -2. Can we put the equal sign? Well, if we look over here, this is still an open circle. There's no actually y of -2 there. That's just the starting point, but not equal to. So we have no equals here as well. So no equals, and that is because there is an open circle. All right, our interval notation, not too terrible. We're finding the range. We're going from negative infinity to -2, never equal to infinity, and we can't be equal to -2. If you want, you could draw little arrows here too, just to show where that parenthesis came from. Okay, one more for you guys to try. This one, it looks like an oval, and the fancy math word for that is an ellipse. Why don't you guys go ahead and try this one as well, and then once you unpause, we will see how you did. Ready, set, go. Okay, smallest and largest outputs. Well, we'll start with the x's, and we just go along the x-axis, and we say, what's the smallest? The smallest will be furthest to the left. The furthest to the left, I think, is this x of -3. The largest x is furthest to the right. That's +3. All right, what about the y's? Well, my smallest y, right, small y's occur as you move down the y-axis. Looks like it's a y value of -1. And the largest y is a y value of +1. Notice I put in closed circles here. If you don't see an open circle or a gap, then we always assume that the points are closed. So you could put any sort of closed circles along this function. So we have these closed circles moving along here. Okay, this one's actually a little bit easier than what we've done before. The set notation is a little more complicated though, but it's something you've seen before, so it shouldn't be too much of a surprise. The reason it's a little more complicated is because we need to explain that the x's are between -3 and +3. So although one way you could do this is you could say x is greater than or equal to -3 and x is less than or equal to +3. We've learned before that the fancy, cool way to write this is we say that we put -3, then x, then +3. We can put all this together with the and. And then notice which way these inequalities are facing. This first one has the mouth facing the x, and the second one has the point facing the x. And so the way you're normally going to see this is -3 is less than or equal to x, which is less than or equal to +3. And it just means that you can use any x between -3 and +3, right? What's an x between -3 and +3? Well, 1. Is there a point on this graph that has an x of 1? Sure, here and here. There's actually two different points, 1 comma something, 1 comma something. All right. Let's go ahead and try the interval notation, which again is a little easier this time. Domain, we're going from -3 to +3. Then we just have to decide square brackets or parentheses. Well, we are allowed to be equal to -3. There's a closed circle there, and we're allowed to be equal to +3. This is one that just uses square brackets both times. Let's try the range. It's going to be pretty darn similar to the domain. So, Range-wise, we're going to skip, well, no, we can write it out first. So range. Two ways to put this. We can say that the y's can be greater than or equal to -1, and the y's also have to be less than or equal to +1. The fancy way to put all this together, -1, 1, and y, greater than or equal to y, less than or equal to 1, and there we go. The y's have to be between -1 and +1. Interval notation, not too bad, from least to greatest, and we can be equal to both of those, so square brackets. All right, one last little note here. Graphs which are not functions, right, bringing this back to a function thing, fail what's known as the vertical line test. All right, now I say they fail the vertical line test. All right, this is when you can draw a vertical line, and don't forget a vertical line is a line that goes straight up and down. It has an undefined slope. And it's when that vertical line passes through more than one point on the same graph. So if we take a peek up here, right, if you put a vertical line anywhere on this first one, my vertical line only touches 1 point. Only touches 1 point. That tells me that this first graph is a function. And I think that even happens on the second graph as well. However, does that happen on the third graph? Well, I think if you drew a vertical line straight through this endpoint, it only touches 1 point. But pretty much anywhere else besides those two endpoints, aren't we going to pass through 2 different points? As soon as you pass through more than 1 point, we say that we have failed the vertical line test. And if you fail it, that tells us the graph is not a function. The reason failing the vertical line test means a graph is not a function is because the line passes through the same x value more than once, but with different y values. And we can again see that up here, right? If I wanted to take these 2 points, this is the point 2 comma, I don't know, let's call it 1.75, and this one is 2 comma, oh no, let's call it 0.75, awkward, 2 comma negative 0.75. And so you ask yourself the same question. If I told you an input of 2, could you tell me the one output that goes with goes with it? And the answer is no, because there are 2 different outputs that go with it. This is a graph that is not a function. It's still an okay graph. We just need to realize that this would be defined as a relation, not a function. So at the bottom it says, which relation fails the vertical line test? You could go ahead and try to draw that ellipse over here. And then if you wanted, if you had the room, you could even draw your line, right? It passes through 2 or more points. Okay, at this point you've really gotten everything you need out of this lesson. The last part of today is just to get you guys some practice. So I have 8 problems for you. The first 6 are discrete, and then the last 2 are some continuous practice. So good luck with each of these. If you have time, once you're done, you should check your answers, and you can just skim through this video quickly. If you're in class, you guys can share them out if you'd like. And that is just about it for today. So you do need to have this finished. And then, of course, this is a new unit. You do have independent practice this evening. It's very short. It's more practice, right? The more we practice something, the more likely we are to remember it. So I wish you the best of luck. The end of this video is just me going through it. So hopefully everything goes fast. Ready, set, go. All right. Hopefully you're back and ready to go, and I'm just going to move through this one pretty darn quickly. If I do move through anything too quickly, please leave me a comment. Let me know which questions you need more detail on, and I can edit this. All right. First off, is this relation a function? I think yes, it is. Each x value has its unique, or each x value has a y value and only one y value. Right, you'll notice that these 2 x's go to the same y, but that's okay. Think Portus ups. You can have 2 different numbers that map to the same output. It would only not be a function if this -1 went to 2 of them. So yes, it is a function. Each input, I guess. And notice I knew the inputs because this is domain. So each input has 1 output. Perfect. Given an input, what's the output? Well, an input of 0 gives us an output of 3. Given the output, what was the input? Well, if you have an output of 5, there are two possible inputs, negative 1 and 1, but it's okay working backwards. There is a definition that tells us that if you work backwards and you only have an individual x for every y, then that's known as a one-to-one function, but you don't need that for this year. Domain and range, nothing too terrible. We're just going to take our domain, range, and we're just going to copy what's up here. Negative 1 through 3. And the range is 3, 5, 11, 21. Nice. Second one. See, these really are not bad. Function or not a function? Nope. What are the ones that break it? I think the only one that breaks it here is 0, right? 0 maps to both negative 2, but also to 1. Everything else, 1 only goes to one spot, 2 only goes to 1, 3 only goes to 1. Given an input of 0, what are the outputs? Well, negative 2 and positive 1. Given the output, what's the input? Well, an output of 1 could map to 0, or it could map to 2. Domain and range. And I'll zoom in at the end. This looks like 0, 1, 2, and 3. And our range, negative 2, 1, 2, and 4. It's nice when they write it in order for us. All right, moving on. Let's look at this from a table. Is this relation a function, y or y not? Well, I'm just going to check the inputs, which are the x's. Negative 3 only appears once, negative 2, 1, and 5. Every x only appears once. Yeah, this has to be a function, right? Each x has a single output. Given an input of 1, what's the output? Well, the input of the x's, so the output is 1. Given an output of 1, what's the input? Well, that one's trickier because there are 4 different outputs, or 4 of the same outputs of 1. So we actually have 4 possibilities here. Negative 3, negative 2, 1, and 5 could all be the x's. We use those braces when we list a whole bunch of numbers. Domain and range, we're going to remember this. The domain is the x, and that's pretty nice there. The range is the y, and that's a really easy one because there's only one y value. Moving on through. Alright, this is now a discrete relation from a set of points, so it looks like I have 1, 2, 3, 4, 5, 6 points. Is this a function, y or y not? Let's check each of the x's. There's a 4 that goes to 8, negative 3, 2, oh, here's another 4. I see 2 different 4s, or 2 of the same 4s, and this 4 goes to a different x. There's another 3 that's okay, and a negative 8. So yeah, I think there is an issue here. We're going to say no, and that's because we have 4 which goes to 8, and we have 4 which goes to negative 3. That is a no-no. Given an input of negative 3, what's the output? That's got to be negative 2. Right? We got that from the point negative 3, negative 2. Given an output of negative 3, what's the input? Well, I think there's a few possibilities here, right? An output of negative 3 means we're working backwards here. Output of negative 3, it could be 4. Okay. However, I think it also could be 3. And that's okay. We can have the same output matched to multiple inputs. Last but not least, domain and range. We're getting good at this. Domain. Hopefully those curly braces are coming along too. Our domain here can be a little obnoxious just because of all the x's, so I'm just going to write them out on the side. 4, we have negative 3, we have a 2, we have a 3, we have a negative 8. Should be 1, 2, 3, 4, 5, 6, minus 1 because the duplicate. There we go. Negative 8, negative 3, 2, 3, and 4. Okay. And then our range is going to be that same thing. I'm just going to write out our ranges. We have a positive 8, negative 2, negative 1, negative 3, and negative 5. 5 ranges because 2 outputs repeat. Negative 5, 3, 2, 1, 8. And there we go. Oof, that's a rough one. All right, halfway done. Let's get the others done. Discrete relations from a graph. All right. Given an output of 2, what was the input? Remember, output is the y-axis. So I want to jump up to 2 on the y-axis and say, what input gave me an output of 2? In fact, I think there are 3 different points here. 1, 2, and 3. So if you wanted to write those out, okay, and I'll zoom in over here, you could see that this first one is the point -2 with an output of 2. This point over here is 1 with an output of 2. And this last guy over here is 5 with an output of 2. So I think we have 3 possibilities here. We have -2, 1, and 5 all give an output of 2. Given an input of 1, what's the output? Well, the input is on the x-axis, so an input of 1, what's the output? It looks like 4 to me. Is this relation a function? Well, a nice quick way to do this is just to set up your vertical line test and see if the vertical line passes through more than one point. So here's the first point. The vertical line only touches one point. Only hits one point, 1 point. There's only one here, one here, one here, one here. I think every vertical line only hit 1 point, so this is a function. Because the vertical line only hits 1 point each time, that means that each x has only one y. Domain and range, nothing too bad. We just need to list all the x's and then all the y's. So x's just go left to right. -4, -2, -1, and 0 and 1. And then what else is here? 3 and 5. So again, I just went left to right to get all the x's. To do the range, which I've been doing in yellow, so I should continue. To do the range here, we're going to go from bottom to top. So as I go bottom to top, the first one I get to is -2, then to 0. Okay, and then as I move up, I see 2, happens 3 times, 2, 3, and 4. And there we go. Next one. Given an output of 0, remember an output is a y, so here is, let's see, the y-axis at 0 is moving up, is right here. What is the input? So we're looking for an x here. Well, input of 0 will get you 0, and also an input of 3 will get you 0, right? This is the point 0, 0, and 3, 0. So given an output of 0, what was the input? Well, it's either an input of 0 or an input of 3. All right, let's go the other way. Given an input of 0, what's the output? Okay, well, an input of 0 means you move along the x-axis till you get to 0, and then you're looking along the y's to see what gave you a point. And I think the only point I see along the y-axis is 0, 0. Now the next question says, what point can you remove to make this relation a function? So that tells me this is not a function. Let's see if we can understand why. Vertical line, only touching 1 point, 1 point. Ooh, we're touching 2 points over here. This is a no-no. So this makes this not a function. We have the point 3, 2 and 3, 0. If I said the input is 2 or the input is 3, could you tell me the exact output? No, because there are 2 different outputs. So, what do? Well, they said, what point can you remove? It's actually up to you. You could either remove 3, 2, and that would be fine, or you could remove 3, 0. You need to remove one of them. And so I'm just going to put both. I'm going to say 3, 0, or you could remove 3, 2. Domain and range, nothing too bad. Our domain here, we do the same thing. We just run along the x-axis. -3, -2, -1, 0, 1, and then 3. Okay. And then our range, we do the same thing, but we go bottom to top. So I'm moving up my y-axis. I get to -3 first. Oh, I guess I forgot -3 on the x's. Sorry. There we go. So we start at the bottom. We get -3. And then as we move up, 0, 1, 2, 3, 4. All right. Let's finish off class with our 2 tricky problems down here, these continuous graphs. First off, given an output of 0, what was the input? Remember, the outputs occur on the y-axis. So an output of 0, I move up the y-axis till I get to 0. That's right here. And then I move over. This is the point, negative 3 comma 0. So an output of 0 was created by an input of negative 3. If we wanted to go the other way around, given an input of 0, what's the output? I roll along the x-axis till I get to 0. And it looks to me like the output is going to be negative 1. Write the domain using both notations. Okay, well, to set this up for the domain, what I really like to do is think, what is the smallest x and the largest x? So as we move along the x-axis, I think the largest x we come to is an x of 3. Right? This is the point 3 comma something. So my largest x was 3. What's the smallest? The most negative? Well, as you move to the left, on here, the most negative I see is negative 5. But they have this arrow, right? This arrow goes forever and forever and forever. So thinking about the x-axis, here's negative 6, negative 7, negative 8, negative 9. I think because the arrow goes to the left domain, we always think left and right. Because it goes to the left infinitely far, I think the furthest we get is negative infinity. So two ways to write this. One way is with those cool less than or greater than signs. And we don't need to include infinity there. We just use 3 and everything smaller. So one way we can write this is that x is less than or equal to 3. Equal to because we have a closed circle. If we wanted to use our interval notation, we go least to greatest. We can use 3. We cannot be equal to infinity. Let's try the range. Okay. As we do the range, we do the same thing, but we work from bottom to top. So we think, okay, what's the smallest y we ever get to? I think the smallest y we ever get to, the lowest the function goes, we think about tall and short this time, or the maximum and the minimum of this function. The lowest we ever get looks to me to be a negative 2 on the y. And then we move up. Notice on this graph, the highest it looks like we ever get is, I don't know, like 0.75, something like that. But again, this graph goes up and up and up forever. Because it goes there, there's going to be a 1, there's going to be a 2, 3 is going to be on there, 4, 5. I think this goes infinitely tall, and so the highest that will ever be there is positive infinity. So I'm seeing the smallest was negative 2, the largest is positive infinity, and so we should write that out. Our domain, nope, sorry, this is the range, this is the y, silly, silly. We start at negative 2 and we go up, so I think our y values are greater than or equal to negative 2. In terms of this interval notation, we start at negative 2, end up at infinity. We can be equal to negative 2, but not to infinity. Last but not least, again, it might be kind of hard to see on your paper, so just zooming in, we have a closed circle up here at the x value of 2, y value of 1, and we have an open circle down here that has a y value of negative 4 and an x value of negative 3. Okay. So given an output of negative 1, what was the input? So the output is negative 1. Output is always the y-axis. What was the input? Well, I think to get to this point that's on our graph, our input was 0 to get an output of negative 1. Given an input of negative 1, what was the output? Well, the input's negative 1. The output then is on the graph, looks like negative 2. Domain and range time. It's sometimes easier when your graph doesn't have arrows because you can kind of physically see the largest and smallest values, but we'll do that for x first. For the domain, as we roll along the x-axis, what's the smallest x that ever happens? Well, there's no negative 5, no negative 4, but negative 3 occurs, right? Negative 3 is on here, and negative 2, negative 1, 0. So I think negative 3 is the smallest, and it looks like it ends over here at positive 2. So we go from negative 3 all the way up to positive 2. Well, how do we write that? One way we can write it is we can say, and I'll do the two separate ones just so you can see it all together. My x's can be equal to negative 3, and they have to be smaller, I shouldn't have said equal, greater than negative 3, and also smaller than 2. Can they be equal to both of these numbers? Well, negative 3 has an open circle, so no, x can't be equal to negative 3. However, 2 has a closed circle, so we can be equal here. Remember, the fancy way that we put this all together is we have the negative 3, the x, and the 2. The point is pointing towards the x with the equal sign and 2. The mouth is towards the x over here. So this is the much more common way to write what I did up here. They both mean the same thing, though. And then, if I wanted to write this in our interval notation, we go from negative 3 to 2. I can be equal to 2. I can't be equal to 3. Negative 3. Let's try those y's, and that's it for the day. So, the smallest y we get to, right, we think about our y-axis here. The smallest y occurs near the bottom of the y-axis. It looks like it's going to be negative 4. That's the lowest my graph ever gets on the y-axis. The highest my graph ever gets is positive 1. So putting this all together, let's see if we can just skip right to our fancy range here. We have negative 4, 1, and y. We know it looks like less than signs for each of these. Can y be equal to both of those? Well, y can be equal to 1. There's a closed circle. I don't think y can be equal to negative 4. There's an open circle. And if we wanted our interval notation, we have negative 4 to 1. We can be equal to 1, but not to negative 4. So that concludes our lesson for today. Hopefully you feel pretty confident on the idea of domain and range and this input-output function thing. You will, of course, have your daily quiz next class. Not a surprise, no groans. Bring your notes, do your independent practice, and you'll find tons of success. So thank you again for joining me. I'm excited to have you back next class for lesson 3.2.